Hi, everybody. Glad to see you again. And let's continue our previous lecture about vibration isolation. Okay, one second, please. And today, our lecture number 16, and it's called Sensor Systems in Engineering. And let's back to the main idea first. Imagine we have a simple example of force isolation and motion isolation are shown in figure C and D. It's a center of this slide. And we obtain the transmissibility or force transmissibility function for system in figure C. Then, in view of equation, the motion transmissibility of the system in figure D is equal to the same expression. First, consider the force transmissibility problem on figure C, which is shown on figure E. We adopted it. And this might represent a simplified model of machine 2 and its supporting structure. Clearly, the elements M, B, and F are in parallel. Check yourself and tell me if you agree or not. Right. Since they have a common velocity v across them. Hence, its mechanical impedance circuit is shown in figure F on the bottom part of this one. In this circuit, the impedance of the basis elements are as Z sub M, yes, equals MS or MJ omega. Z sum B equals simply B. Z chi is K over S or K over J omega, right? So all of these mass, strain, and damper, we may transform in according to time domain model, their impedance, and mobility. Substitute the element impedance into the force transmissibility expression, which is obtained by using the laws of element interconnection shown in this slide, and circuit in previous figure F. Figure F, as you can see on the bottom part. Okay. So we get this first equation on the top. This expression is obtained by dividing the numerator and the denominator by F. Now, use the part that K over M is equal omega n squared and B over M equal 2 omega, say omega n, or omega n is undamped nature of frequency of the system, simply square root from K over M. And that here it's a damping ratio. And we divide A through the omega n square, and we can get the second equation here. You can see for the TF. After transmission and transcription, when we have the B over 2 square root from chi M, it's say the damping ratio of our system. After that, our TF can transform into this more simple form, more rational form, right? So the transmissibility function has a phase angle and magnitude. In practical applications of vibration isolation, it is the level of attenuation of the vibration excitation that is of primary importance, rather than the phase difference between the vibration excitation and the response. Accordingly, we use the transmissibility magnitude, as we can see here on the third equation. To determine the peak point for T sub F, differentiate the expression within the square root of sine A and equate to 0. As you can see at this first equation on the top. The equation should be equal zero, as we can see on the right side. And hence, this simplifies to next expression here. Its roots are equal 0, and the r square equals this expression. The root for r equal 0 corresponds to the initial stationary point, generally speaking, at 0 frequency. That does not represent a peak. Taking only the positive root for r square and then its positive square root, the peak point of the transmissibility magnitude is given by this next expression here for r on the center of this slide. For small theta, Taylor series expansions give our next expression. Very simple, 1 plus 4 theta squared. So with this approximation, equation evaluates to 1. And hence for small damping, the transmissibility magnitude will have a peak when r equals 1. And from this equation, its values can be as a final expression here. So the absolute value for TF will be proportional for this expression. 1 for 2 theta over 2 theta. The 5 curves of absolute value for T sub F versus for R when theta equals 0, 0.3, 0.7, and 1, and even 2 are shown in this diagram. These curves use the exact expression and can be generated using the following MATLAB program. From the transmissibility curve in this figure, we observe the following. And first of all, there is always a non-zero frequency value at which the transmissibility magnitude will peak. And this is the resonance, peak or resonance, right? And second, for small theta, the peak transmissibility magnitude is obtained and approximately when we have r equal 1. As theta increases, this peak shifts to the left for lower value for peak frequency. And 3, the peak magnitude decreases when theta increases, and we can see decreases peak magnitude when theta exceeds. All the transmissibility curves pass through the magnitude value 1 and the same frequency when r equals 2. The region of isolation when the T sub F absolute less than 1, between 1 and 0, 1, is given by when r given 2. So this part we have or here over that right of. And 6, In the isolation region, the transmissibility magnitude decreases as R increases, and we can see R increases and T sub F is decreasing, right? So, in two particular situations, from the transmissibility curve, we observe the following these next two expressions. And we can see on the top of this slide, when T sub F absolute no more than 1.5%, and R is simply square root for all theta. And second, when T sub F absolute no higher than 0.5 for simply 50%, but R may be this, and this value for specific theta value. And next, suppose that the device in our figure has primarily undamped natural frequency of 6 Hz and damping ratio only 20%, 0.2. Suppose for proper operation, it is required that the system achieves a force transmissibility magnitude of less than 0.5. Operating frequency value greater than 12 Hz. In this case, we need this second equation. And we can see we have this equation. For theta equal 0.2 and R as 12/6 get us 2, this expression computes to the 2 in power 4 minus 2 times 2 in power 2 and minus 12 times 0.2 in power 2 times 2 in power 2 minus 3. These values get us 3.0.8. It's higher than this, right? And hence, the requirement is met. In fact, since for R equal 2, the expression becomes in this our next expression here. 2 in power 4 minus 2 in power 2 minus 12 in power 2 4 theta squared minus 3 and get us 5 minus 48 theta 8. And it follows that requirement for would be met for 5 minus 48 theta squared. It's a positive value. From this case, theta must be less than square root from 5/48, or simply theta equals 0.32. If the requirement was not met, say theta equals 0.4, an option would be to reduce damping. In design problems of vibration isolation, what is normally specified is percentage isolation as given by this bottom expression. I for isolation, its absolute value 1 minus P absolute, and all times for 100%. For the result, for our equation, exactly here on the top, this corresponds for I in this diagram. The isolation curves are plotted, namely in this diagram. These curves are useful in the design of vibration isolation. But we should note the model in our figure F is not restricted to sinusoidal vibration. Any general vibration excitation may be represented by a Fourier spectrum, which is a function of frequency omega. I hope you remember that. And then the response vibration spectrum is obtained by multiplying the excitation spectrum by the transmissibility function T capital. The associated design problem involves the selection for the isolated impedance parameter K and B to meet the specification of isolation. Another application of component interconnection and impedance matching is mechanical system concerned speed transmission. It may be gears, harmonic drives, lead screw nut devices, belt drives, rack and pinion classical devices, and many others. For a specific application, consider a mechanical load driven by a motor. Often, direct driving is not practical owing to the limitation for the speed torque characteristics of the available motor. By including a suitable gear transmission between the motor and the load, it is possible to modify the speed torque characteristics of the drive system as felt by the load. This is a process of component interconnection, interfacing, and impedance matching of mechanical systems. We will illustrate the application of these concepts using an example. Okay? So let's see our example. Consider the mechanical system where a torque source, in our case torque source is a motor of torque T and moment of inertia J sub M is used to drive a purely inertial load of moment of inertia J sub L. Okay? What is the resulting angular acceleration Q of the system? We should neglect the flexibility of the connecting shaft. Now, suppose that the load is connected to the same torque source through the ideal, it means loss-free gear of motor to load speed ratio. So, as shown this in figure B on the right side, where R is equal to 1. What is the resulting acceleration Q in this case? Theta double dot sub J of load. Obtain the expression for the normalized load acceleration. Load acceleration is A proportional theta double dot J over theta double dot in terms of R and P. P is a relation between J sub L over J sub L. Sketch A versus for R for P equal 0.1, 1, and 10. Determine the value of R in terms of P that will maximize the load acceleration R. So let's start our solution. For the unit without the gear transmission, Newton's second law gives for us this equation of the torque. In the brackets we have J sub M times J sub L times theta double dot equals T. And hence the theta double dot proportional T, and we have on the bottom J sub M plus J sub L. So for the unit with the gear transmission, and see the free body diagram shown in this figure, in the case of a loss free, it means 100% efficient, gear transmission, and Newton's second law gives us as this equation on the left. Here the d sub g is the gear torque on the load I know. By eliminating d sub g in equation, we get this expression for theta double g dots here on the top. Divided by this equation for theta double u dot, and we get this expression. And you might see it's a right corner, and we get as this expression. We get the transmitted acceleration ratio as A for here, where the P is simply J sub L over J sub M. And from this, note that in case when R equals 0, and for any R that very, very big values up to great value, we have in this case, A will be comes to the 0. And the big value over obtained through the differentiation get us dA over dr. We have this expression, and such should be equal to. We get, by taking the positive root, equation for Rp here, square root from P, where Rp is the value of R corresponding to the peak of acceleration. The peak value over A is obtained by substituting equation Vi, and this we have equation for IP here. It's in nomination, it's 1 plus P. In denominator, 2 square root from P. Also note from equation here, when R equals 1, we have A equal R or 1 for any values of P. And hence, all curves in equation will pass through the same point, and this point will get us as A as the transmission R should be equal 1. In this, we sketches this equation for different P. P equals 10, P equals 0.1, P equals 1. All of them cross in this dot, 1, 1. The peak values are tabulated in this table. You should note it from this figure that the transmission speed ratio can be chosen depending on the inertia ratio to maximize the load acceleration. Hence, the associated impedance matching problem is as follows. For a special or required peak acceleration ratio AP, select R and P using this expression. And Rp is simply, we may write as a square root from P. In particular, we can state the following. All these three expressions. In case when J sub L, the same value as J sub M, pick a direct drive systems, you have in case when R equals 1, or we have no gear transmission. In case when J sub L less than J sub M, we get a peak speed up here as the peak value when R proportional square root for J sub L over J sub M. And so when J sub L higher than J sub M, pick a speed down here at the peak value of R. So now we can make our summary sheet. Component interconnect. Due to dynamic interactions or coupling, the conditions in the components change after interconnection. For effect, change in signals, loading, etc., and loading the signals of the input component change undesirably when an output component is connected. Example of electrical loading: sensor that generates an electrical signal in case when we have input device, and signal acquisition hardware in case for output device. Example for mechanical loading: sense object, the same input device role, and the heavy sensor mounted on it, we get output device. Component interconnection considerations: in this case, impedance matching, signal conversion, and signal conditioning. Impedance: a cross variable to throw variable, applicable in multiple domains, but we should notice electrical impedance is analogous to mechanical immobility or inverse of mechanical impedance matching. Match the impedances of the interconnected devices and add compensating impedances if necessary. Impedance matching categories: source and load matching for maximum power transfer. A second option, power transfer at maximum efficiency. Third, reflection prevention in signal transmission. And fourth, loading reduction. Maximum power transfer uses conjugate matching. You can see this expression on the top. Power transfer at maximum efficiency, and all another category. We can see in this slide. It's only a few we may find as a simple oscillation model for TF, transmissibility magnitude, next one, vibration oscillation, isolated design, mechanical transmission, and the final design problem. And now let's come to another topic of this question of this lecture. It's called data acquisition hardware. You know, engineering systems are digital DAQ for a variety of purposes, such as process condition monitoring and performance evaluation, fault detection and diagnosis, product quality assessment, dynamic testing, system identification, and process control. A typical DAQ system consists of the following key components. First of all, it's sensor and transducer to measure the variables in the process that is monitored. Okay. Second, signal conditioning. It may be filtering and amplification of the sensed signal. Third, DAQ hardware to receive different types of monitored signals and make them available to the bar of a computer. Four, computer. Computer in maybe personal computer, laptop, microcontroller, microprocessor, all of these devices that can process the acquired signal, and so as to achieve the end objective for our DAQ system. Power supply, it may be internal signal conditioning, and active sensor with need power. DAQ power typically comes from the computer. And software. A software, driver software to operate our DAQ hardware for properly acquiring the sensing data. Application software for use by the computer to process the data for the end objective. Consider the process monitoring and control system showing in this next figure. Typically, the measured variable responses or output input of a physical system are available in the analog form, which are signals that are continuous in time. Furthermore, typically the drive signal or control input for a physical system have to be provided in the analog form. And these signals maybe have to be filtered to remove the undesirable components and amplified to bring the signals to proper levels for further use. Filtering and amplification you have been studied in electronic circuits, right? A digital computer is an integral component of a typical engineering system and may take the form of a PC, laptop, or one or even more general purpose multiprocessor with powerful processing capability or more specific microcontrollers with extensive input-output capability. For additional processing power, coprocessors such as digital signal processors may be incorporated. In the system, the digital computer will perform tasks such as signal processing, data analysis and reduction, parameter estimation, and model identification, diagnosis, performance analysis, decision-making, tuning, and control. Essentially, the computer performs the end objective of the monitoring entire DAQ process. Computer architecture and hardware. The computer uses a bus to transfer data between components, so in the computer. In a typical PC, the DAQ card goes into an expansion slot over the computer. The power for DAQ comes from the PC itself. The operation of the DAQ is managed by driver software, which is provided by the DAQ supplier and is stored in the computer. The driver software has to be compatible with the operating system, like Windows, Mac OS, or Linux, or another for our computer. This software manages accessing data from the DAQ and making them available to the computer for further processing. This further processing is done by application software, which may be programmed using such tools as MATLAB and LabVIEW, or using high-level programming languages such as C, C#, C++. This software not only will process the acquired data to achieve the end objective, but also may be used to develop a suitable graphical user interface for the monitoring system. Motherboard. The motherboard or main board or system board of a computer represents interconnected key hardware components of a computer. External device and input-output ports are also connected to the motherboard through a computer bus. Various IC packages and other hardware devices are mounted on the motherboard, which is located in the computer house. Other devices, it may be various cards, including DAQ, are mounted in the expansion slots of the computer house. I mean the tower computer, big computer. But for another case, we have a special device. A typical architecture of a computer motherboard is shown in this figure. It shows the main components such as the central processing unit or CPU, memory, and clock. Expansion slots for hardware such as DAQ, network card, video card, storage, sound card, and memory expansion card. And here are some acronyms that are used in the context of computer hardware operation and communication. SCSI. It's a small computer system interface. Standards and protocols for connecting and transferring data between computers and peripheral devices such as hard drive, CD drive, and scan. EISA, extended industry standard architecture. A bus standard for PC. PC bus, a popular bus of a PC for connecting hardware devices in it and data transfer between them. Internal bus, a bus for connecting the internal hardware of a computer, also known as system bus and front side bus. Maybe you hear external bus. This is a bus for connecting external hardware to a computer, also known as expansion bus. USB, this universal serial bus, a computer bus for connection and communication with various peripheral devices. FIFO, first in, first out. This is method for arranging data in a buffer or stack, where the oldest data are processed first. DMA is a direct memory access capability where a hardware component in the computer can directly access the computer memory without going through the CPU. Okay? UART is Universal Asynchronous Receiver and Transmitter. TCP/IP, it's a Transmission Control Protocol. TCP is a co-communication protocol of Internet Protocol IP. This is a protocol for network communication, more reliable at the expense of speed. And another one interesting, UDP, User Datagram Protocol, a communication protocol in the IP suite, faster at the expense of reliability. And now let's study data acquisition and analog to digital conversion. Input to a digital device, typically a computer or a microcontroller, and output from a digital device are necessarily present in the digital form. And hence, when a digital device interfaces with an analog device, like sensor or actuator, the interface, hardware, and associated driver software help to perform several important functions. Two of the most important components of interface hardware are digital to analog converter, DAC. As you can see here, DAC, digital to analog converter, and analog to digital converter, ADC. An analog signal has to be converted into the digital form using as an ADC, according to an appropriate code before it is read by a digital processor. For this, the analog signal is first sampled into a sequence of discrete values, and each discrete value is converted into the digital form. During this conversion, the sample discrete value has to be maintained constant by means of S over H hardware. If multiple signals from multiple sensors are acquired simultaneously, an analog or digital MUX, as you see here, may have to be used to read the multiple signals sequentially by the computer. On the other hand, a digital output from a computer has to be converted into the analog form using DAC. For feeding into an analog device, such as drive amplifier, actuator, or analog recorder, or maybe even display. So DAC, ADC, and MUX are studied in this section. Both ADC and DAC are elements or components in a typical DIQ card, or sometimes called input-output board. Complete DIQ card and associated driver software are available from the such companies as National Instruments, Adlink, Elijah, Precision Microdynamics, and many others. A DIQ card can be directly plugged into an expansion slot of a PC and automatically linked with the bus of the PC. Its operation is managed by the driver software, which has to be stored in the computer. Powerful microcontroller units have DIQ functions and hardware already integrated into them. Usually 14 digital input-output pins, and 6 of which are for the pulse width modulated output. 6 analog inputs with a built-in analog to digital converter. The main components of DIQ card are shown in this figure. The MUX selects the appropriate input channel for the incoming analog data. The signal is amplified by a programmable amplifier before ADC. As discussed in a later section, the S/H samples the analog signal and maintains its value at the sample level until the conversion by the ADC is complete. The P4 element stores at the ADC output until it is accessed by the computer for digital processing. The DIQ card can provide an analog output through the DAC, so that we have a DIQ card here on the right. And furthermore, a typical DIQ card can provide digital output as well. An encoder can be directly interfaced to the DIQ card for use in motion control applications. Specifications of typical DIQ cards are given in this slide. Many of the identified parameters are discussed in this earlier. Others are either self-explanatory or discussed elsewhere in the lecture. Particular note should be made about the sampling rate. This is the rate at which an analog input signal is sampled by the ADC. The Nyquist frequency or the bandwidth limit of the sampled data would be half this number for a sampling rate of 100 ks over 50, and it is 50 kilohertz. When multiplexing is used, the effective sampling rate for each channel will be reduced by a factor equal to the number of channels. For example, if 16 channels are sampled simultaneously, the effective sampling rate will be 100 kHz over 16. It caters 6.25 kHz over second, giving Nyquist frequency as a cut from this 3.1 to 5 kHz. Since DAC and ADC play important functions in engineering applications of monitoring, they are discussed now. DACs are simpler and less expensive than ADC. And furthermore, some types of ADCs employ a DAC to perform their function. For this reason, we will discuss DAC before ADC. The function of a digital to analog converter, DAC or DA or D2A, is convert a digital word stored in its data register, called DAC register, typically in the straight binary form, into an analog value, voltage, or current. In this manner, a sequence of digital data can be converted into analog signal. Some form of interpolation has to be used to connect and smooth the resulting discrete analog value for forming the analog signal. Typically, the data in the DAC register are arriving from the data bus of the computer to which the DAC is connected. Each binary digit in B binary digit, right, of information in the DAC register may be presented as a state of a bistable, bistable, or two-stage logic element, which can generate a voltage pulse or a voltage level to represent the bit. For example, The off state of a bistable logic element or absence of a voltage pulse or low level of a voltage signal or even no change in a voltage level can be represented as a binary signal, right? Conversely, on the state of a bistable device or presence of a voltage pulse or even high level of a voltage signal represent binary parts. The combination of these bits, which forms the digital word in the DAC register, will correspond to a numerical value of the analog output signal. Then, the purpose of the DAC is to generate an output voltage or signal level that has this numerical value and maintain the value until the next digital word in the arriving digital data sequence is converted into the analog form. Since a voltage output cannot be arbitrarily large or small for practical reasons, some form of scaling would have to be done in the DAC process. This scale will depend on the reference voltage that is used in the particular DAC circuit. A typical DAC unit is an active circuit in form of an IC chip. It may consist of a data register, solid-state switching elements, resistors, and op-amps powered by an external power supply, which can provide the reference voltage for the DAC. The reference voltage will determine the maximum value of the DAC output. As noted earlier, the IC chip that represents the DAC is usually one of the many components mounted on the printed circuit board, which is the TIQ card or input-output card or interface. This card is plugged into a slot of the port of this. The typical operation of the DAC chip is based on turning on and off of the semiconductor switch at proper time, as governed by some logic dependent on the digital data value. This switching will determine the output of an op-amp circuit, which is the analog output of DAC. There are many types and forms of DAC circuits. The form will depend mainly on the DAC method, manufacturer, and requirements of the user or their particular application. Most types of DAC are variations of two basic types: the weighted type, or summer type, or adder type, and the ladder type. The ladder type of DAC is more desirable and more power efficient, even though the former type would be somewhat simpler and less expensive. Another straightforward and simpler method uses a pulse width modulator, PWM chip. Two representative DAC methods are outlined now. The measured variables of an engineering system are typically continuous in time. They are analog systems. However, common applications that use these signals, such as performance monitoring, fault diagnosis, and control, will require digital processing of their signals. Hence, the analog signals have to be simple as discrete time points, and the same values have to be represented in the digital form, according to a suitable form, to be read into a digital system, such a computer or a microcontroller. An IC device called analog to digital converter, IDC, is used to accomplish this. A feedback control scenario, which involves both DAC and ADC, is shown in this slide. Sampling as analog signal into a sequence of discrete values introduces aliasing distortion. This error can be reduced by increasing the sampling rate and also by using an anti-Aliasing filter. Nevertheless, according to Shannon's sampling theorem, the frequency spectrum of the analog signal beyond half the sampling frequency or Nyquist frequency is completely lost due to the data sample. And furthermore, in representing a discrete signal value by a digital value, or an error called quantization error is introduced due to the finite bit length of the digital. This is also the resolution of the ADC. DACs and ADCs are usually situated on the same DAQ card, as you can see for this figure. It's on the right side, DAQ card. But the ADC process is more complex and time-consuming than the DAC process. And furthermore, many types of ADC use DAC to accomplish the ADC. And hence, ADCs are usually more costly, and their conversion rate is usually slower in comparison to these. Two common types of ADCs are discussed now. Some other related versions are considered at the end of our lecture. And now let's see successive approximation ADC. This ADC uses an internal DAC and a comparator. The DAC input starts with the most significant bit and change. The DAC output is compared with the analog data until a match is found. It is very fast and is suitable for high-speed applications. The speed of conversion depends on the number of bits in the output register of the ADC, but is virtually independent of the nature of the analog input signal. A schematic diagram for a successive approximation ADC is shown in this slide. You should notice DAC is an integral component of this ADC. The sampled analog signal is applied to a comparator like a differential amplifier. Multiple a start conversion control pulse is sent into the control logic unit by the external device that controls the operation of the ADC. Then, no new data will be accepted by the ADC unit. A conversion complete pulse is sent out the control logic unit. Initially, the registers are clear so that they contain all 0 bits. Okay, and then the ADC is ready for its first conversion approximation. The first approximation begins with a clock pulse. Then the control logic unit sets the most significant bit and MSB of the temporary register to 1. All the remaining bits that register bin 0. For example, if the FS there we have 12 volts, so the DAC output now is 6 volts, which is compared with the analog value, which could be anything in the range from 0 to 12 volts. This digital word in a temporary register is supplied to the DAC. If the comparator output is a positive, the control logic unit will keep the most significant byte of the temporary register at binary 1 and will proceed to the next application. In case, if the comparator output is negative, the control logic unit will change the most significant byte to binary 0 before processing to the next approximation. The second approximation will start at another clock pulse. This approximation will consider the second most significant byte to the temporary register. In this manner, all bits in the temporary register are set successively starting from the most significant byte and ending with the LSB. The computer will not read the register if a data valid signal is not present. And hence, the total conversion time is approximately n times the conversion time for one bit. Typically, one bit conversion can be completed within one clock period. Signal value and sign, it should be clear that if the maximum value of an analog input signal exceeds the first signal value of a DIC, then the excess signal value can be converted by the ADC. The excess value will directly contribute to the error in the digital output of the ADC. And hence, this situation should be avoided either by properly scanning the analog input or by properly selecting the reference voltage for the internal DAC unit. Thus far, we have assumed that the value of the analog input signal is positive. If the value is negative, the sign has to be accounted for in the ADC by some means. For example, the sign of the signal can be detected initially from the sign of the comparator out, when all bits are zero. If the sign is negative, then the same AD conversion process as for a positive signal is carried out our switching the polarity of the comparator. And finally, the sign is correctly represented in the digital output, and after the conversion, the digital number corresponding to this offset is subtracted from the converted data in the output register to obtain the correct digital output. And then we may assume that the analog input signal is positive. Also known that the delta sum, delta F, ADC or delta sigma ADC, this popular variety of ADC has a relatively low cost, low bandwidth, and high resolution. The basic principle of the device is shown in this figure. The sample analog data value is compared with the integrated output of a 1-bit DAC. If the difference is positive, the comparator generates a 1-bit. Otherwise, it generates a 0-bit, and the conversion as stored in the temporary register is complete and available for reading by the computer. Hence, the digital worth in this register increases from 0, 1 bit at a time, until the value equals the analog sample value. The term delta is used because the digital value in the register is incremented by 1 bit at a time, corresponding to the output of the 1-bit ADC. And also because the compared analog value is incremented 1 bit at a time, corresponding to the output of the 1-bit DAC. The word sigma is used because the delta values are added to form the digital output. Greek uppercase sigma is normally used to denote summation. There are several other variations of delta sigma ADC. In them, typically, the integrator is located in the forward part of the feedback loop after taking the difference between the sample data value and the output of the 1-bit DAC. Then, the 1-bit ADC generates a bit stream whose bit density represents the sample data value. Data signal is recovered through the demodulation. As example, amplitude modulation, frequency modulation, pulse width modulation, and pulse code modulation. Sidebands, a frequency component, usually sinusoidal, when multiplied by a carrier sign is shifted to either side of the carrier frequency. Amplitude demodulation multiplies the amplitude modulation signal by 2 over AC cosine. Carrier aided modulation, its modulated signal rides on a carrier, or sometimes called as a power, more power. So spectrum is equal carrier spectrum plus sideband. Delta sigma ADC sample analog value is compared with integrated output over 1 bit DC. If difference positive, comparator in 1 bit ADC generates 1 bit. Otherwise, it generates 0 bit, and conversion is complete. And now we will be starting as a new topic of lecture, performance specification and rating parameters. You know, an engineering system consists of an integration of several components, such as sensors, transducers, signal conditioning, and modification devices, controllers, and a variety of other electronic and digital hardware. The performance and realization of intended purpose of the overall system depends on the performance of the individual components and how the components are interconnected. All devices that assist in the intended functions of an engineering system can be interpreted as components of the system. Activities related to the system instrumentation and operation, such as prescription of the components for the system, selections of available components for a particular application, design of new components, analysis and evaluation of the system performance, making adjustments, parametric structure, and others to the system, control the system. The performance requirements have to be specified or established based on the functional needs and associated constraints of the overall system. Then, these specifications have to be correlated and established in terms of the rating parameters or performance parameters of the individual components. Some performance parameters are found in the product data sheet, which can be obtained from the manufacturer or vendor. For new developments of products, the required performance specifications have to be developed by the product development team in consultation with the users, regulatory agency, vendors, and so on. In this part of the lecture, we study ratings and parameters for performance specification of components in an engineering system, which in turn determine the performance of the overall system. Typically, the performance of an engineering system is specified under 3 important types of performance measures. First, speed of performance, second, stability, and third, accuracy. Performance parameters in all 3 types are discussed in this lecture. As expected, due to the dynamic interactions in an engineering system, there is some degree of interrelations among parameters of these 3 types. 2 categories of parameters are found in the performance specification of components in an engineering system. First, parameters used in engineering practice, and second, parameters defined using engineering theoretical consideration, and a reference model either in time domain or in the frequency domain. For performance specifications in the analytical domain, 2 types of dynamical models are used. First, differential equation models in time domain, and second, transfer function models in the frequency domain. Specifically, the parameters for performance specification are commonly developed using these two types of dynamic models. Models are quite useful in representing, analyzing, designing, evaluating, operating, and controlling such devices as sensors, transducers, controllers, actuators, and interface hardware, including signal conditioning and modification devices. Measuring devices or sensor systems, which include sensors and related hardware, are an important category of components or subsystems in the instrumentation of an engineering system. Their performance may be specified with a reference to a perfect measuring device. A perfect measuring device can be defined as one that possesses the following main characteristics. And first, the output of measuring device instantly reaches the measured value. First response for zero error. Second, transducer output is sufficiently large. Third, the device output remains at the measured value. It may be zero error without drifting or getting affected by environmental effects. The output signal level of the transducer varies in proportion to the signal level of the measurement. 5. The connection of a measuring device does not distort the measure itself. 6. Power consumption is small. All these properties are based on dynamic characteristics and therefore can be explained in terms of dynamic behavior of the measuring device. In particular, items 1 through 4 can be specified in terms of the device response. First, we discuss the response characteristics that are important in the performance specification of a component of an engineering system. And let's start with dynamic reference model. As noted earlier, in engineering applications, both static parameters and dynamic parameters are used in performance specification. Dynamic performance parameters for a device concern dynamics of the device. For example, perfect requirements are never precisely realized for a sensor, perhaps in view of the sensor dynamics. For instance, the sensor will have a delay in providing its final reading due to the sensor dynamics. Dynamic performance parameters are established with respect to a dynamic model, which represents the dynamics of a considered component or subsystem, like sensor or sensor system. It may not be a complete and precise model of the device, but rather a model representing the performance specification. And hence, it is a reference model. However, the dynamics of the reference model has to be related to the dynamics of the actual device, or a precise model of it. Two types of dynamic models are used. First, differential equation models in the time domain. And second, transfer function model in the frequency domain. Time domain model can be converted into transfer function model and vice versa by means of a simple operation. It's like replacing the time derivative equation by the Laplace variables and vice versa. However, for practical reasons or significance of the performance parameters in the two domains, it is important to consider models in both domains. The widely used reference models for a component are first is a first order model, and second order or simple oscillator model. Both first order and second order models have to be considered because a complete second order model cannot be constructed by cascading two first order models. Notably, the cascading first order model will always result in an overdamped model. which cannot represent oscillations that commonly and naturally occur in the device dynamics. A first-order linear dynamic system is given in time domain this first equation on the top. Tau times u dot plus u y, y dot plus y proportional k. Tau is the time constant. K here is the direct current K. The corresponding transfer function model is made in the next equation here. Y from S over U from S, it gets us H from S. Or maybe write the classical automatic control expression, transfer function K over tau S plus. Suppose that the system starts from Y with 0 and get us Y naught, and a step input of magnitude is A capital is applied at the initial state. The corresponding response is get us here this expression for Y step. This response is sketched in our first figure here. It's stop Y step here. The first term of the RHS of activation free response. And the second time is a forced response. It should be clear that a significant parameter of performance specification using a first order model is the time constant tau. The simple oscillator is a versatile model which can represent the performance of a variety of devices and specify the desired performance. Depending on the level of damping that is present, both oscillatory and non-oscillatory behavior can be represented by this model. The model can be expressed at these first equations here on the top. Omega n here is the undamped natural frequency. Psi is a damping ratio. The corresponding transfer function model is expression on the next, y over u. It's here. It's a transfer function. But we should notice that we have normalized the model by making the static gain equals to 1. However, we can simply add a gain k to the numerator and this equation, if necessary. The damped natural frequency is given by here equation for omega damp. The actual or damped system executes free or natural oscillations at these frequencies. Natural oscillation, omega n. The response of the system to a unit step excitation with 0 initial conditions is known as the Y step. Here we can Y step here, where the psi at the end is the phase angle in the response and is given by equation for cosine psi equal simply this. Next lecture, we will continue and study performance specification and rating parameters. And now, I hope you enjoyed this lecture, and I'm looking forward to see you next time. You know, I want to say we have only 2 final next 2 lectures, 17 and 18. Okay, see you later. Bye.